Hello, everybody, and welcome back to another Geography 340 Climatology lecture. I am Dr. Zach Hilgendorf, and as I alluded to in the last video, today we're going to be talking about the seasons. More specifically, we're going to be talking about what are the seasons, what defines the seasons, and what causes the seasons. So let's start off with the simple ones. Well, what are the seasons? We know them as spring, summer, autumn, and winter, right? Well, let's get into what defines those seasons and what causes them. So here we can see basically a video of our Earth breathing, if you want to call it that. These are annual pulses of vegetation and land ice. Now, this is a really cool one because it shows over the year how that ice expands and contracts, how vegetation grows, basically how our world is changing, and that's all driven by the seasons. Now you might remember in our last video we talked about the ecliptic plane, the perihelion, which is when the Earth is closest to the sun, and the aphelion when the Earth is farthest from the sun. Well, that doesn't really define or severely impact our seasons. What does is our axial tilt and our axial parallelism, which we, like I said, just talked about in our last lecture. So here's a really cool diagram that shows what our planet looks like on its axial tilt relative to the sun. And here we can see it. It'd be winter or astronomical winter in the northern hemisphere and summer in the southern hemisphere. 6 months later, it flip-flops, right? Summer in the north and winter in the south. Same said for comets, which is pretty interesting and intriguing. So let's start off with December, our December solstice, which typically takes place on either the 21st or 22nd of December, depending on the year. Here is what our globe looks like at that point. We might recall seeing something similar to this exact diagram in our last lecture. Here we can see the ecliptic plane. That is our subsolar point. So at this location on Earth, the sun is coming into the Earth at a 90-degree angle, or the sun's rays are coming in at a 90-degree angle. Well, what could that offset be? 23.5 degrees south. We know that, right? So that is 23.5 degrees south latitude. That is the Tropic of Capricorn. Right there. And that's during the December solstice. Our declination, as we say or call it, is 23.5 degrees south latitude. This is the start of our astronomical summer if you are in the southern hemisphere. It's the start of our astronomical winter if you're in the northern hemisphere. So what's the insolation intensity at this point in watts per meter squared? We have to think back a little bit to our previous lecture where we knew that insolation intensity is equal to the solar constant, which is 1,361 watts per meter squared, times the cosine of the zenith angle, or the cosine of the solar angle. Go back and review those topics if you need to refresh yourself on what the zenith and solar angles are. But we know that when the Earth's rays are coming in at a 90-degree angle, we are at 1,361 watts per meter squared. We're at our solar constant, right? But if we step down to 45 degrees south, we're at slightly lower, right? The rays are traveling through more atmosphere because that solar angle is higher. So we're at 1,266 watts per meter squared. Here we're at 66.5 degrees south latitude and 995 watts per meter squared. And here we are at 90 degrees south latitude, our south pole, at 543 watts per meter squared. Well, what about on the northern hemisphere? What are things looking like up there? Well, at the equator, we're at 1,248 watts per meter squared. At the Tropic of Cancer, we're at 23.5 degrees north latitude. We're at 928 watts per meter squared. At 45 degrees north latitude, right around where we live, we're at 499 watts per meter squared. At 66.5 degrees, we are at 0, right? We're in the Arctic Circle. At certain points of the year, this is receiving no sunlight, which is what we're going to get into next. So we know we can calculate based off of the insolation intensity equation what our insolation is going to be, like what action or actually we have, what energy we actually have to work with, right? Now, let's think back to our 104 days. Here is a figure you might remember. I remember it from my days in Geography 104. I just taught this recently. This is from the Insolation in the Seasons lab, where you were trying to figure out insolation at 5 different cities across our globe. And this is the graph we use to determine longest day of the year. So when it's summer, and it's the summer season for the north or the southern hemisphere, we use this. When it's the winter season, we use this. And what these graphs basically tell us is, okay, for a given season, the day length on the shortest day of the year is going to be relative to its latitude, which makes a lot of sense. And that latitude or that day length is going to change whether you're in summer or winter. So let's look at all of our previous sections or latitudes that we examined in our last little diagram. So the longest day, if you're at that subsolar point, or if the subsolar point and our angle of declination is along 23.5 degrees south latitude, 13.5 hours. We have a day that is 13.5 hours long. Now, if we scoot down to 45 degrees south latitude, 15.5 hours long. We go down even further, 66.5, 24 hours. So at this point in the southern hemisphere, when it's their summer, that Antarctic Circle, if you call it, receives 24 hours of daylight. The equator, 12 hours. The Tropical Cancer, 23.5 degrees north, 10.5 hours. 45 degrees north, our shortest day of the year here in the Eau Claire area or along the 45th latitude, about 8.5 hours long. And then up in the Arctic Circle, perpetual night for a portion of the year, right? We've heard of this before. All right, what about June? Our June solstice, typically around June 20th to 21st. Here we can see that same setup. There is the subsolar point at the June solstice. So there are the rays of the sun are coming in at a 90-degree angle. Angle of declination is 23.5 degrees north. It is the start of our astronomical summer and the start of the southern hemisphere's astronomical winter. So what's the insolation intensity? This exercise should be familiar. There's our equation again. But we don't really have to go through this, do we? Because depending on where the Earth is in its tilt and depending on which hemisphere you're in, on these 2 points, whether you're in the December solstice or the June solstice, these values should look pretty familiar, right? Because we calculated them already, for the most part. And that last one in December, if we look at day lengths, they should all look familiar because they're just basically in reverse, right? Okay, well, let's think of something different here. March. Typically, the March equinox is March 20th to 21st. declination is 0, right? The sun's rays at this point are centered right on the equator. And we start to think, well, equinox, equator is a good giveaway, but what does equinox mean? Well, if we remember back, equa, obviously, is we see this in words like equidistant, equilateral, equal, right? It means that something is equal. Well, if we look at that word nox, Latin, I believe, night, or sorry, light, pardon me, not night. So basically, equinox, equal light. It's kind of, if you look at the roots of those words, is a dead giveaway. It means that we have equal light and equal dark on that day of the year, 12 hours of daylight and 12 hours of night. That's the start of our astronomical spring in the northern hemisphere and the start of our astronomical fall in the southern hemisphere. So now let's think about our insolation intensity again. Start here, 13.61 watts per meter squared, right? That's when it is a 90-degree angle to our equator. If we step up to 23.5 degrees north, 1248 watts per meter squared, 962 watts per meter squared, 543 watts per meter squared, and 0 watts per meter squared. All right, what about day length? Well, it's 12 hours along the equator. It's 12 hours along the Tropic of Cancer, 12 hours at 45 degrees north, and 12 hours at 66.5 degrees north. So let's look at that word down there in the left-hand corner, equinox. So what does that mean? Now, this is actually a good hint on why we have 12 hours on this day during our equinoxes. It's the center point between the longest and shortest days of our year. If we think about that, if we average those days out, the shortest and longest day at a given latitude, you also get 12 hours. So equa, you've probably seen that root before, equidistant, equilateral, close enough, equal, the word equal. Well, that's what it means. It means equal something. Nox is basically the word meaning light. So equinox, equal light, means that you have to have equal dark. So you have 12 hours of daylight and 12 hours of night. So that's one quick, easy way to remember what your day length hours are going to be on any given equinox. Alrighty, moving on to our last one here. This is September 22nd or 23rd is when this equinox falls on. Autumn in the northern hemisphere or spring in our southern hemisphere. And let's think about what this would be, or what these values and day lengths would be relative to the other three positions, maybe one in particular. Let's think about what it would be compared to March. Well, it's going to be the exact same thing in our September equinox. And why? Well, let's think back to that equinox word again. It's equal light. That means that we have the same amount of day length, which indicates that pretty likely we have the exact same amount of insolation intensity at every given spot. So whether you're in September or you're in March, either equinox, those values are going to be the exact same. So to summarize, we've talked about insolation intensities and day length hours on our December and June solstices and our March and September equinoxes. In the next couple slides, we'll just kind of check over our knowledge here. All right, so to start, what is declination on December 21st or 22nd, the December solstice? You can take a second to pause if you need to look back at your notes. It's going to be 23.5 degrees south. That the sun's rays will be encountering the Earth at a 90-degree angle at 23.5 degrees south during the December solstice. What about the March equinox, 21st of March? Take a second to pause if you need to. At the equator. During the June solstice, 21st to 22nd of June, 23.5 degrees north latitude. And during the September equinox, 22nd to 23rd of September, 0. What's declination right now? What will declination be in a month? And these aren't answers that I will be able to provide. You have to think of where we are. You can use our closest proxy. We just passed through fall, so you have a good idea of what they were on September the 22nd or 23rd. And then what about day length, right? Think about how day length changes through the years. Now, if we were to look at December 21st to 22nd, it's 12 hours along the equator, 0 hours along the pole, or the North Pole, and 24 hours along the South Pole. Same thing, but 12, 12, and 12 in our March equinox. Flip-flopped in our June equinox, or solstice, pardon me. And then the same in our September equinox. You can think, what's the day length in Eau Claire today relative to whatever day you're working on? You have to think, what will the day length in Eau Claire be in a month? So when we look at the seasons, we can kind of think of a couple key descriptors here. So in December, high noon sun, long days. In the southern hemisphere, low noon sun, short days in the northern hemisphere. Flip-flopped, high noon sun, long days in the northern hemisphere in June, low noon sun, short days in southern hemisphere. And this doesn't really apply to the tropics, because between those two tropics, we're basically just moving around that same point. They don't really have defined seasons like we do in the higher latitudes. All right, so let's talk about total daily insolation. So TDI is equal to F, that's denoted by F, which is a function of insolation intensity and day length. So the TDI for a given latitude is equal to the average daily insolation intensity times the day length. So the average daily insolation intensity is approximately equal to the solar constant, so that 1,361 watts per meter squared, times sine of the noon sun angle divided by 2. Units of TDI are watt hours per meter squared. So 1 watt hour per meter squared is equal to about 3,600 joules. Surprise, surprise, it is random homework time. So you're basically going to be working to fill in this table. You might have remembered something from this in Geography 104. So on the leftmost column, you'll see latitude. So we have the equator, and then 23.5, 45, and 66.5 degrees for the north and southern hemispheres. And you're going to be calculating the December solstice total daily insolation, the June solstice TDI, and the equinox TDIs, and the annual TDI range. So use our lectures, use the notes that you've gained from these lectures to be able to calculate these different rates using the equation we just talked about and those angles of declination, etc. Then you're going to answer 2 questions with this. So first off, where should the smallest annual temperature range occur? At which latitude that we've looked at here? And then where should the largest annual temperature range occur? At which latitude? So you're going to go through those and you'll be submitting that on Canvas. So to recap, we talked about what are the seasons, what determines the seasons, and what causes the seasons in this video. We will be moving on to bigger and brighter things as we go into these next few lectures. So I hope you enjoyed, and I hope you have a great day. Thank you.